right, we're going to take a look at arc length with parametric functions and then get into vectors. So we've already seen the arc length formula for continuous functions. This is for x ranging from a to b, including both of those. This was something we looked back a couple of units ago. A lot of the questions that we dealt with arc length, they had really complicated antiderivative techniques involved. In fact, most of them we just ended up using a calculator to evaluate. And it was really just being able to set up the correct expression to find the arc length. If you were to take y equals f of x and actually parameterize that, or write that as x of t equals some function, y of t equals some function, I'm not going to go through all of the steps because there are about a bajillion different explanations and proofs of this. You can actually rewrite this same expression in parametric form to be the following. So it's almost the exact same formula. The only difference is instead of a 1, we have a dx dt all squared. And instead of dy dx, we have dy dt all squared. Also, keep in mind that we are integrating with respect to t. So that means that the limits of integration, here I changed from a to b to c to d. Here, this is a range of values of t. So here t is starting at c and ending at d. So we're going to look at a couple of examples of those worked out in class. I just want you to get really familiar with the formulas there. All right, so let's shift gears rather. Let's take a look at vectors. So this is something you've probably seen in physics and other math classes, but just a refresher. A vector is just a directed line segment. Every vector has direction and magnitude. Usually we give a name of a vector with a little kind of arrow thing up top. So there's vector u. Now, every vector has what we call components. So for this vector, I have an x component and a y component. And typically we write those vectors in what's called component form. So it's just like writing a point in the xy plane, an ordered pair. The big difference is we have those angle brackets. So if ever you're working a problem, doesn't matter where, when, or how, and you come across something with those angled brackets, that is a way to indicate to you, hey, this is a vector, not just a regular function or anything else. Okay, so every vector has direction and magnitude. Magnitude is the length of a vector. So looking at that right triangle we just formed up there, those of you who had geometry with me, remember that Pythagorean theorem. If I wanted to find the magnitude or the length of that vector, I could use Pythagorean theorem. So magnitude of this vector, and I'm going to call it a position vector for the moment, this is just using Pythagorean theorem, x squared plus y squared under a square root. So that is what we call the magnitude of that vector. Now, you're going to see some notation where they put these double lines around your vector's name. That's just another way to say the length of a vector. So we're going to come across a lot of problems where we might need to plug in a t to get an answer, or I should say a constant value of the magnitude of some vector. Okay, so let's think calculus terms. In calculus, we look at position, velocity, and acceleration. So I named this thing a position vector. So let's say that u is some vector that represents the position of something in the xy plane at time equal to t. If I wanted to find the velocity, I could just take the derivative of each component function. So I changed the name from u to v. So the velocity vector would be x prime of t comma y prime of t. Then if I wanted to find the acceleration, you probably guessed it, I take another order derivative. The acceleration is the second derivative of x, comma, second derivative of y. Most of the time, these are all going to be functions that depend on a parameter. Usually t, could be s or r, whatever. But most of the time, we're going to see t as our parameter. So let me just show you a quick example of this. So suppose I have a particle. Now we've seen particle motion on a line. It was just a particle moving either back and forth or up and down. We haven't really seen particle motion in the plane. So this is just some particle moving all around the xy plane. And to figure out where that particle is at time equal to t could be whatever, I get this vector function. 3t squared minus 6t would be my x component. And then t squared minus 8t plus 9 would be my y component. this question is asking me to find the velocity, the speed, and the acceleration of that particle moving around in the plane in all kinds of ways, modeled by the x and the y functions up there, whenever t is equal to a 4. So velocity, take derivatives. Okay, so v of t is going to be the derivative of my x function, comma, derivative of my y function. So I just use my power rule there. You're going to come across all kinds of functions. You got to remember all your derivative rules, which tells me that at t equal to 4, I can just plug right in. 4 times 6 minus 6 is 18. 2 times 4 minus 8 is 0. Okay, so there's my position. I'd be 18 on the x-axis and then 0 in the y direction. Now, the second part of that, it says speed. So remember that velocity is speed in a given direction. Velocity can be negative. You could be traveling backwards relative to some position. Speed is the absolute value of your velocity. Another way to say that is the magnitude of your velocity. So what we're going to do is find the magnitude of my velocity vector and then plug in a 4. So speed is magnitude of velocity, or absolute value. Absolute value and magnitude are really the same thing. It's just absolute value is typically a one-dimensional thing that we look at, and magnitude is a two-dimensional, or actually, for those of you taking higher level math classes, an n-dimensional thing that we measure. So I can use Pythagorean theorem, and I get this, 6t minus 6 all squared plus 2, okay, yada, yada, yada. And then I can plug in a 4, but you're going to notice, oh, I could have just taken the magnitude after I plugged in a 4 to find my velocity. That works just as well. So it turns out that my speed in this case is going to be 18, whereas my velocity is 18 comma 0. So you might think, wait, that's like the same thing. Kind of. 18 is my speed, which can go really in any direction, but my velocity is telling me I'm moving over 18 in the positive x direction, and I'm not moving anywhere in the y direction. Kind of a subtle difference. The velocity tells me also a direction at the same time. So I've got velocity, I've got speed. Now I need acceleration. So I just take the derivative of my x component function and my y component function, plug in a 4. Fortunately, my acceleration just comes out to be constant. So I just get 6 comma 2. And I just wrote that as a of 4. Just turns out that since I get a constant for my x and y, it doesn't matter what I plug in for t. In fact, I have nowhere to plug in t. That's just this problem. There are going to be problems where you can plug in the t, and you will want to do that. That's actually going to wrap up this video.